Hello everyone, welcome to a boring introduction of arrays. Arrays are one of the most basic data structures in computer science. It is a sequential data structure. This means that the data is stored adjacent to one another in computer's memory. This is also known as contiguous memory allocation. Here we have an example of an array. Here we have 4 elements in the array, so the size of the array is 4. The index of an array is used to tell the location of element in the array, like here, location of A is 0, M is 3, L is 2, Z is 1. Usually arrays are 0 index, that is the first element resides as 0 index and so on. Arrays find a vast application in computer science. Arrays can be used to represent tree data structures, specifically heaps. Instead of using nodes with pointers, a heap can be efficiently represented as an array, where the parent-child relationships are determined using index calculation. Then we have sorting algorithms. Algorithms like insertion sort, merge sort, heap sort, quick sort all rely on array as their primary data structure. Arrays are naturally suited for searching algorithms as well. When an array is sorted, binary search, a highly efficient logarithmic time search algorithm, can be used to find elements. Even with an unsorted array, linear search provides a simple, though less efficient method for finding elements. Now, arrays come in a different types and variations. The most basic form is the one-dimensional array, organizing elements in a single row, something like this here. Then we have multi-dimensional arrays, that is, multiple arrays inside a bigger array. It is used to represent metrics and tables. So here on this side, you can see we have rows, and on the top, these are called columns. We also have jagged arrays in some languages, which allow for rows with varying number of elements. Nowadays, it is pretty common to have dynamic arrays supported by different languages. While the traditional array have a fixed size, many programming languages offer dynamic arrays or lists, which can resize themselves dynamically as needed. This is not the case with your plain old arrays, where you have to tell the size of the array during creation of the array. Now let's talk about the performance of the array. To understand the performance of any data structure, we need to look at different operations. These operations are reading, searching, insert, and deleting. When we measure how fast the operation is, we don't compare times directly, but the order of operation, or simply the number of steps required to complete the operation. We will discuss this more when we study big O notations. Now let's get back to the performance of an array. Reading from an array is a one-step process. This is because, as mentioned earlier, arrays are sequential data structures. So if you know the address of the first element, the address of other elements can be calculated by multiplying the index by the size of each element, which is why we can access them directly using their index. Now searching is a little bit different from reading. In reading, we give an index of element that we want to read. When it comes to searching, the computer has to look through the array to find the index of the element. In this example, if we told the computer to search for element M, the computer would have to start from A and then look through all the elements, and then finally when M is found, it will return 3. Again, this is because the computer stores the memory address of the first element of array in program's memory instead of each element, because that would be very expensive. What we described here is basically a linear search algorithm, as the computer needs to go through each element in the array one by one. If the element we are looking for is not found in the array, the steps taken will be equal to the size of the array, which is 4 in our case. This means the efficiency of linear search algorithm is proportional to n, where n is the number of elements. So if this array was of size 10 and the element that we are looking for is not found in the array, we would have to look through 10 elements. So basically, the searching is proportional to the number of elements in the array, whereas the reading operation was constant time. That is, no matter how big the array is, reading will take constant time. Now let's talk about insertion. Now the speed of operation for inserting an array depends on where we are adding the value. If we were to add the value at the end, it would be a one-step process, because the computer can calculate where this element should go, again by using the same thing, that is, multiplying the index, which is 4, by the size of each element. But please note that if the array is of fixed length, the computer would have to create a bigger array, that is, array of size 5, and then move all the 4 elements into the new array. So these values will be moved to the new array, and here we can add the new value. Let's just say it's p. So if the size was fixed, we are moving these values. The computer first creates a bigger array and then has to move the elements to the bigger array. Now, if we were to add the element to the front of the array or in between somewhere, that is somewhere here or in between here, the computer would have to move the elements. So M would be moved to here, L here, Z here, A here, and then finally P can go here. Similar is the case if we were to add it between A and Z. So in the worst case, this operation can be seen as n plus 1 operation, where n is the size of the array. N represents the number of moves or the number of steps we took to move the elements, and 1 is for adding the element that we were going to add. Now let's move on to delete operation. So deleting is somewhat similar to insertion. To delete an element from an array, it is really simple. You can just delete it. Like if we wanted to delete L, we can just remove it from here. But the empty space left behind is not something that we want. This is because arrays are not very efficient when there is empty elements between other elements. So we would have to fill in the space by moving M to here. And if there were more elements, we would have to move them to the left by 1. The order of operation would be first delete the element, then move other elements around to fill the gap. This means n plus 1 operations again. So to summarize arrays, arrays are fundamental data structure in computer science used to store collection of elements of same data type. They are often the most efficient way to store and access sequences of elements in memory. This contiguous storage allows for direct access to any element in a constant time using the index of the element. Arrays have minimal overhead because they don't have to store extra information like pointers to link elements together. There are few limitations associated with arrays. One of the main limitations of traditional arrays is their fixed size, which must be known at time of creation. Once created, the size cannot be changed. This can be problematic if you need to store unpredictable number of elements. To address this issue, many new languages come with dynamic sized arrays. As we saw, while accessing an element by index is fast, inserting or deleting elements, especially in the middle of an array, can be inefficient. This is because it might involve shifting subsequent elements to make room for new element or close the gap left by the deleted element. To sum it all up, arrays are a powerful tool for organizing and managing collection of data. Their simplicity, efficiency in element access, and versatility make them a cornerstone of computer programming. However, understanding their limitation, particularly regarding size and efficiency of an insertion or deletion, is essential for choosing the most effective data structure for a given task. That's it for this lesson. I hope you enjoyed it. If you have any questions, please post a comment under the video or reach out to our Discord server. Until next time, happy coding!